Hello and welcome to this revision session on paper 2 for AQA A-level physics. So what we're going to do in this revision session is we're going to look at answering examination style questions for A-level physics paper 2 for AQA. So if we've been successful and we've learned in today's revision session, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics and understand what topics we need to improve upon for A-level physics. So how should you carry out this revision session? Well, when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. And when you're doing this, make sure you write out in full sentences and show your full working out. Whilst on the right hand side in this section, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. And at the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising AQA A-level physics? Well, the first step you should be doing in your revision is learning the key facts. So use revision guides, class workbooks, student prep notes, a textbook to learn the key ideas of the course, and you might wish to make mind maps or write out notes yourself. Then secondly, test yourself. Use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. Then finally, in the step 3 is use exam prep books, homework books, supervised study books, workbooks to answer exam questions and then mark your own work, and you may wish to download your own examination past papers to do this. So the steps of learn the key facts, testing yourself and practicing exam style questions is the way to revise AQA A-level physics. So let's start off by looking at thermal physics. So in the following question, it says figure 1 shows how the temperature of water is maintained in a hot tub. The hot tub system has a volume of 4.5 meters cubed and is filled with water at a temperature of 28 degrees Celsius. The heater transfers thermal energy to the water at a rate of 2.7 kilowatts while a pump circulates the water. Assume no heat is transferred to the surroundings. So calculate the rise in water temperature that the heater could produce in 1 hour, and then the pump can circulate the water at different speeds. When working at higher speeds, the rise in temperature is greater. Explain why. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular first question? Well, you've got to remember what our equation is when we have a temperature rise in a situation, and that is that we would say that E equals MC triangle T. Now, we want to here work out triangle T, so what we would do is we'd rearrange this and we'll make triangle T the subject. So you can see quite clearly that triangle T, or delta theta as is written down here, is equal to E over m times by c. Now it's important to note that in this particular question you're given the power and you're given the time, so we can use this to work out what the energy is, because we should know that energy is equal to power times by time. But there are two issues with this particular question. Firstly, time is given in hours, so you've got to convert that into seconds by doing 60 times by 60, because we work in seconds in physics, not in hours. And then secondly, you're given the power in kilowatts, so you've got to once again convert that into watts by saying it's 2.7 times 10 to the 3, because kilo means times 10 to the 3, to then work out what your power is, and energy equals power times by time, so you can work that energy out. We know what our value for C is because it's given in the question, 4,200, and we know what our value for the mass is because once again it tells you that the volume of water is equal to 4.5 meters cubed, and in the question it tells you that the density is 1000. So therefore you can say that because density is mass over volume, well therefore mass is density times volume, so you can work it through, pop all the numbers in, and you get an answer to be 0.51 Kelvin. Now how can when working at higher speeds the rise in temperature be greater? Well, you've got to think about what's going on, because when the pump is working and it's pumping the water around, the pump is doing work on the water, it's putting energy into the system. So what this means is that this work can raise the temperature of the body because of the first law of thermodynamics. Energy is going into the situation and it's not changing state, so therefore it must be the kinetic energy store of the object which is increasing, so therefore that is shown as the temperature of the body. Also, you can say that this links in because we know that the mean squared speed is directly proportional to the temperature. We know that from the equations given in the equation book, so we can say that when the mean squared speed goes up, as indicated in the question, that the temperature must go up as well. Let's now have a look at some questions to do with nuclear physics. So the first question says an alpha particle with a kinetic energy of 4.9 MeV is directed towards the center of a gold nucleus of radius r, which contains 79 protons. The alpha particle is brought to rest at point S, a distance r from the center of the nucleus as shown. So firstly, calculate the electrical potential energy in joules of the alpha particle at point S, and then secondly, calculate the distance of closest approach of the alpha particle to the nucleus. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, what you've got to remember is that we would say in this situation the kinetic energy of the alpha particle is turned into the electrical potential energy when it is repelled by the gold nucleus, and it will be repelled because they're both positively charged. So we can say that if you're starting off with 4.9 MeV of kinetic energy, then it's going to turn into 4.9 MeV of electrical potential energy. But the issue is it wants the energy to be in joules, so the question's pretty much asking you to convert from MeV into joules, and we know that 1 eV is 1.6 times 10 to the minus 19, so therefore 1 MeV is 1.6 times 10 to the minus 13, because M means times 10 to the 6, so you would do 1.6 times 10 to the minus 13 times by 4.9 to get 7.8 times 10 to the minus 13 joules. Now, to work out the distance of closest approach, what you've got to remember is that electrical potential energy is charge times by electrical potential, and electrical potential is Q over 4 pi epsilon 0 r. Both equations are given in the examination booklet. So therefore we can say that electrical potential energy is going to be Q1 times by Q2 over 4 pi epsilon 0 r. We can then rearrange it and make r the subject, so say r is Q1 Q2 over 4 pi epsilon 0 times by electrical potential energy. Now in the previous question we worked out the electrical potential energy in joules, so we can pop that into the equation. Now we know that the charge of the object is going to be, for the alpha particle, if you notice, it's going to be 2 times by 1.6 times 10 to the minus 19, because there are 2 protons in the alpha particle, and then for the gold nucleus it tells you there's 79 protons, so it's 79 times by 1.6 times 10 to the minus 19, because remember each proton has a charge of 1.6 times 10 to the minus 19. Pop the values in and you get your answer to be 4.67 times 10 to the minus 14 meters. The next question says, determine the number of nucleons in the gold nucleus, where you're given the radius in R0. Then it says the target nucleus is changed so it has 1 fewer proton. The alpha particle is given the same kinetic energy. Explain without further calculation any changes that occur to the distance r and ignore any recoil effects. So pause the video now, then unpause the video when you want to go through your answer. Right, so this question is asking you to use the equation r is equal to r0 a to the power of a third. Now in this question you're given r and you're given r0, so at this point you need to work out a. So you would say that a is equal to r over r0 to the power of a third. We'll just rearrange the equation and we've worked out our value through to be a to be equal to 197. Now a is the number of nucleons, so that is your answer. Now, in this next question, what's going to happen to the distance of closest approach? Well, if we think about it, we're saying r is equal to q1 times by q2 over 4 pi epsilon 0. So just from thinking of that calculation, if the value on the top, q1 times by q2, is going to be lower because one of them has less protons, okay, that tells us that our value for r is going to decrease. Now if you think about it in terms of kinetic energy, well, if there's less protons in the nucleus, then there's going to be less of a repulsive force between the nucleus and the alpha particle, so therefore it can travel further, okay, before the repulsive force causes the same kinetic energy to turn into electrical potential energy. The next question says, the core of a thermal nuclear reactor contains a number of components that are exposed to moving neutrons. State what happens to a neutron when it's incident on the moderator, say what happens to a neutron when it's incident on a control rod, and then a slow moving neutron is in collision with the nucleus of an atom of the fuel which causes fission. Describe what happens in the process. So pause the video now, then unpause the video when you want to go through your answer. Right, so what happens when a neutron is hit by a moderator? Now it's important to know what the role of a moderator is. The moderator is there to slow the neutron down so it can be absorbed by other fissile nuclei. So what happens is the neutron will undergo an elastic collision and bounce off the moderator with less kinetic energy. That's a very important idea, that the moderator slows down the neutrons via collisions. Now you've got to understand that a control rod works because it will absorb a number of the neutrons to stop them from encountering any more fissile nuclei. So what happens with the control rod is that the neutron is absorbed. Now in the next question it says that a slow moving neutron is in collision with the nucleus of an atom of the fuel which causes fission. What will happen? Well, you've got to think about the different steps. So the first step is that the neutron is absorbed by the nucleus, so a uranium-236 nucleus is formed. This then causes the unstable nucleus to fission, and that produces several nuclei, and it also releases some fast-moving neutrons, and some energy is released as gamma photons. The next question says, a thermal nuclear reactor produces radioactive waste. So state the source of this waste and discuss some of the problems faced in dealing with the waste at various stages of treatment. So your answer should include the main source of the most dangerous waste, a brief outline of how waste is treated, and then problems faced in dealing with the waste, suggestions for overcoming these problems. So pause the video now, then unpause the video when you want to go through your answer. Right, for this type of question, because it's a 6-mark question, you should really try and answer each bullet point individually as its own paragraph. So let's just have a look at some of these answers, which a lot are just factual knowledge you've just got to learn for the course. So for the first bullet point, it's the idea that the highly radioactive nuclear waste is the fission fragments from the fission process, because what you tend to find is the fission fragments, the daughter nuclei produced, are actually going to be very radioactive themselves. So that is actually going to be the most dangerous part of the waste. Now the second part asks you to pretty much talk about what the process is for dealing with nuclear waste. So remember, the first thing is to put the waste in cooling ponds of water. That's for 2 reasons. Number one, it's to cool down the very hot nuclear fuel rods, but also to shield people around it from any alpha particles given off by these particular these rods. Then the plutonium and uranium is separated in a reprocessing plant and then is recycled into further fuel rods. The high level waste left behind after this process is then vitrified, so it's made into solid glass, and then it's placed into stainless steel or lead or concrete cylinders and bunkers, which are stored deep underground. So it's very, very important that you say it's deep underground, and in the UK it's monitored very carefully as well. Now the last question, if you notice, asks you to talk about problems faced with dealing with the waste and how we overcome it. So let's think about what the case is. So like mentioned before, the waste produced is initially very hot after the fission process, and so it has to be placed in water or cooling ponds to cool down, and it's also very radioactive, so the water is also used to shield people from this dangerous radioactivity being given off by the waste. The waste also, if it's in a liquid form, can leak into the surroundings and get into our food chain and our water supply, which is not ideal, as you can imagine. So we vitrify the face, we turn it into glass, so that means that it can't actually leak out and it can't get into our food supply, our food chain, or our water supply. Now another issue is that the waste will be radioactive for hundreds and hundreds of years, or even thousands of years. So we need to store this waste in a stable situation so it isn't actually then knocked out or then put into the food chain or the water supply at a later date. So we need to store them in geologically stable areas, not areas which undergo earthquakes or have volcanoes. And finally, the last thing is the idea that transporting the waste can present a danger to the public, so you make sure you've got to have it enclosed, so even if there is a crash, then the waste will not leak out and people could be contaminated by the waste. Right, the next question says, calculate the binder energy in MeV of a nucleus of 5927 cobalt. You are given the nuclear mass in U. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, what you've got to do is you've got to work out the mass defect of the situation. So what we know is that we know the nuclear mass of cobalt itself because it's given in the question. Now we can also work out what our value is going to be when we're just considering the nucleus with it is separate components. Now we're told in the question, now we've got 27 protons there and we've got 59 nucleons. That tells us we must have 32 neutrons in the nucleus. Now you can find the mass value, the nuclear mass in U for the proton and the neutron in your equation booklet, so it isn't given in the question. So what you do is you work out the total the total mass of all the protons in the nucleus. You work out the mass of all the neutrons in the nucleus. You then subtract that total value by adding the two from the nuclear mass that's stated in the question. This will give you your mass defect. This will give you the mass change from turning your protons and neutrons into the nucleus, and then you can work out your binding energy by multiplying that value by 931.5, because that's the conversion factor between U in the mass in U and the energy in MeV. So you should work it out to be that the mass difference in U is 0.5408, and you multiply 931.5 to get your value of 503 MeV. The next question says, a nucleus of iron 59 decays into a stable nucleus of cobalt 59. It decays by beta minus emission, followed by the emission of gamma radiation as the cobalt 59 nucleus de-excites into its ground state. The total energy released when the iron 59 nucleus decays is 2.52 times 10 to the minus 13 joules. The iron nucleus can decay to one of three excited states, so that the cobalt 59 nucleus, as shown in the figure 5. The energy of the excited states are shown relative to the ground state. Calculate the maximum kinetic energy in MeV of the beta minus particle emitted when the iron 59 nucleus decays into an excited state that has an energy above the ground state. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? So you'll note straight away that how much of the total energy is released. It's 2.52 times 10 to the minus 13 joules. You are given that in the question. Now you also note that you've got a value of what it will go to, okay, by beta minus, okay, into an excited state that has the energy above the ground state. So if you look on your diagram, the ground state is 0, so the energy above the ground state is going to be 1.76 times 10 to the minus 13. Now why don't you use one of the other two? Well, you don't, because it's asking for the maximum kinetic energy, so that's going to be the biggest difference. So the other two values will not give the biggest difference because they are bigger values. So you do 2.52 times 10 to the minus 13 minus 1.76 times 10 to the minus 13, so therefore you would get 7.6 times 10 to the minus 14 joules. Now the question wants it in MeV, so you've got to go backwards and convert it back into MeV, and remember 1 MeV is equal to 1.6 times 10 to the minus 13, so you divide it by that value to get 0.48 MeV. The next question says, following the production of the excited states of 59 cobalt, gamma radiation of discrete wavelengths is emitted. State the maximum number of discrete wavelengths that could be emitted, and then calculate the longest wavelength of the emitted gamma radiation. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one, how do you work out the maximum number of discrete wavelengths? Well, it's equal to the number of differences between the actual energy levels. So what you would do is you would go from energy level 1 to ground state, energy level 2 to ground state, energy level 3 to ground state, then you'd have energy level 3 to energy level 2, energy level 3 to energy level 1, and energy level 2 to energy level 1, all the possible differences. So when you count up all those values, the number of possible differences is 6, so you would get 6 wavelengths, because each wavelength is related to a difference between two of the energy levels given in the diagram. Now calculate the longest wavelength. Now it's important that you remember that C is equal to F lambda. So this tells us that for this particular idea that the longest wavelength is actually linked to the lowest frequency, because when wavelength goes up, frequency goes down, and frequency links to energy. So therefore the smallest energy is going to be the lowest frequency, so therefore the longest wavelength. So what you would do is you would work out the smallest difference fundamentally, so that is from 2.29 to 2.06. that's the smallest difference you can get between any of the values, times by 10 to the minus 13, because it's times 10 to the minus 13 joules. That gives you your smallest energy difference, so therefore we can say lambda is equal to hc over E. We know h, it's Planck's constant, you're given that on the equation booklet. You know c, it's the speed of light, 3 times 10 to the 8, you're given that on the equation booklet. You pop in your smallest difference of energy and you get your longest wavelength, which is 8.7 times 10 to the minus 12 meters. The next question says, the age of the moon has been estimated from rock samples containing rubidium and strontium brought back from the moon landings. Rubidium 8737 decays to strontium 8738 with a radioactive decay constant of 1.42 times 10 to the minus 11 per year. So calculate in years the half-life of rubidium. So pause the video now, then unpause the video when you want to go through your answer. Right, for this question, think about what you've been given. You've been given the decay constant and you need to work out the half-life. So if you look at your equation book, you'll notice that half-life is equal to log 2 over the decay constant. So we know log 2 is 0.693. We're given the half-life per year in the question, so you pop the values in and you get a chance to be 4.9 times 10 to the 10 years. The next question says, a sample of moon rock contains 1.23 milligrams of rubidium. Calculate the mass in grams of rubidium that the rock sample contained when it was formed 4.47 times 10 to 9 years ago. Give your answer to the appropriate number of sig figs, and then calculate the activity of a sample of 8737 rubidium of mass 1.23 milligrams. Give an appropriate unit for your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so for this one, you'll notice in the question you have a value for time, okay, and you need to work out mass. So you can use the equation m is equal to m0 e to the power minus lambda t. So again, how can you work out lambda t? Well, in the previous question, you had the decay constant. Now, and then you can also got the time in this particular question because it tells you 4.47 times 10 to 9 years ago. So you got your decay constant, which works it through to get out your value of lambda t like that. You know what your value of m0 is because it tells you it starts off with 1.23 milligrams. So that's 1.23 times 10 to the minus 3. So at that point, you can pop all the values through and you can work your answer out to be 1.31 times 10 to the minus 3 grams. Now again, how many sig figs do you put your question to? Well, you give it to 3 sig figs because all the values given in the question are given to 3 significant figures. Now the next one is ask you to calculate the activity. So what you got to remember is that we know that n is equal to 8.5 times 10 to the 18. Now you can think about where that comes from because it's going to be the mass, okay, and linking it into dividing by 87u, because you can think about where, you know, how your mass is going to be your value of n times by 87u, so you can work it out like that. You are given n in the question, which is the number of, which is, if you think about it, it's going to be the number of atoms which are present. So at that point you work it through and then you can say A is equal to lambda n. You've already got lambda from the previous question, so therefore you can work out A by popping all the values in to be 3.8, and then what's the units? Well, it's activity, so the units of activity per second are going to be becquerels. The next question says, a nucleus of polonium PO may decay to the stable isotope of lead 20882M and then through a chain of emissions through the sequence of alpha, beta minus, alpha. Figure 13 shows the position of the isotope 20882 lead on a grid of neutron number n against proton number z. Draw 4 arrows on figure 13 to show the sequence of changes to n and z that occur as the polonium nucleus is transformed into 20882Pb. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you've got to remember is in these types of graph, what's the change to the neutron number and what's the change to the proton number in alpha decay and beta decay. So in alpha decay, because you're losing 2 protons, 2 neutrons, in those instances the number of the neutron is going to go down by 2 and the number of the proton is going to go down by 2. Now you'll notice that the position on the graph you're given is the one at the end, so we're going to have to work backwards in essence. So we're going alpha and we're going back up like that because it's after the decay, so we're working backwards. So you've got your alpha like that. Now in beta minus, what's actually happening? Well, in beta minus decay, what do we know? Well, in beta minus decay, we know that a neutron is turning into a proton plus a beta particle and an antineutrino, but that's irrelevant for this particular question. So we can say that if a neutron is turning into a proton in beta decay, then therefore the neutron number goes down by 1, the proton number goes up by 1. So you can see it in the diagram there. Now, the next question says, a nucleus of the stable isotope 20882 lead has more neutrons than protons. Explain why there is an imbalance between the proton and neutron number by referring to the forces that operate within the nucleus. Your explanation should include the range of forces in which particles are affected by those forces. So pause the video now, then unpause the video when you want to go through your answer. Right, now this question is really linking to stuff you did in particles, but it's asking about why you get stability in the nucleus between the protons and the neutrons. So it's the idea that the interaction involved is the strong nuclear force, and that affects protons and neutrons. It affects anything made from quarks, so it'll affect all your nucleons. Now your strong nuclear force has an attraction up to about 3 or 4 femtometers, but it's repulsive below about 0.8 1 femtometer. Now, electromagnetic repulsion will only act between the protons because they're charged and the neutrons are not. But the electromagnetic force has an infinite range and acts across the whole nucleus. So what the idea is that you need more neutrons to hold the nucleus together, because what they will do is they will increase your strong nuclear force because they will experience that, but will not experience the repulsive electromagnetic interaction, so will therefore hold it together in a more stable fashion. So it's important to note that the more neutrons will make it more stable. So what does that mean? It means that the binding energy per nucleon has increased, because binding energy per nucleon is a measure of nuclear stability. Let's now have a look at some questions on magnetic fields. So the first question says, figure 8 shows a step-down transformer used in a laptop power supply. Firstly, explain the purpose of the core in the transformer. Then describe and explain 2 features of the core that improves the efficiency of the transformer. Then explain why transformers only work continuously when supplied with an alternating current. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So in the first one, you've got to understand what the core of the transformer is. So the core is there to ensure that the linkage from the primary coil is interacting with the linkage of the secondary coil. So the core is there to focus, direct, guide the magnetic field round from the primary to the secondary. So it's making sure that you've got your flux from the primary coil linking to the flux of the secondary coil. Now, what 2 features of the core will improve the efficiency of the transformer? Well, there's actually 3. The first one is you make your core out of soft iron, because this allows the magnetic field of the core to alternate easily. Because if it struggles to alternate as they've got your alternating current passing through it, you will get hysteresis and energy will be lost out of the core. Another thing is you want to reduce eddy currents that are induced in the opposite direction in the core due to Lenz's law. So what you would do is you would laminate the core, which is pretty much mean cover in an insulator. So even though you'd have the same change in the magnetic field and you'd have that same potential, well, that same EMF induced, the current will be lower because the resistivity in the actual core is higher. And then finally, the same thing was mentioned before, you could make it out of a high resistivity metal, so even though you've got the same induced EMF, the actual eddy current produced is going to be less because it's a higher resistivity material. Now explain why transformers work continuously only when supplied with an alternating current. Well, it's because an induced EMF is produced by a change in magnetic flux linkage. That is Faraday's law. So the alternating current will produce a change in magnetic flux linkage because it is going, the The alternating current produces a magnetic field that goes backwards and forwards, so you get your change of flux in the core. The next question says a primary coil of the transformer is connected to a 230 V RMS AC supply. The current in the primary coil is 0.3 amps RMS and the secondary coil has 300 turns and provides an output of 20 V RMS and a power of 65 watts. Calculate the number of turns on the primary coil and calculate the efficiency of the transformer. So pause the video now, then unpause the video when you want to go through your answer. Right, in the first question you've just got to use the transformer equation which is given to you in the equation booklet, and that is that MP over VP is equal to NS over VS, where P is the primary and S is the secondary. Now you're given in the question NS, it tells you the number of turns on the secondary coil, 300. It tells you the potential difference or the voltage of the primary. It tells you that it's going to be 230, and we've also got the potential difference or voltage of the secondary. It tells you it's 20 from reading the question. So you pop all the values in and you work out to be 3,450 turns. Now the next question is looking at efficiency. Now you should be aware that efficiency is the useful power out over the total power in. Now it tells you in the question the useful power out, which is the power of the secondary, because the secondary is the output of the transformer. It tells you 65 watts in the question. Now you can work out the input power, the power in the primary coils, because you know that P equals VI. You've got V is 230 from the question, I is 0.3 from the question, so it'll be 230 times by 0.3 to give you your power in, so you work it out to be 0.94. The next question says a cyclotron has two D-shaped regions where the magnetic flux density is constant. The D-shaped regions are separated by a small gap. An alternating electrical field between the D-shaped regions accelerates charged particles. The magnetic field causes the charged particles to follow a circular path. So derive an expression to show the time taken by a proton to travel around one semicircular path is independent of the radius of the path, and that the maximum radius of the path followed by a proton is 0.55 meters and the magnetic flux density of the uniform field is 0.44 teslas. Calculate the maximum speed of a proton that leaves the cyclotron. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one you've got to prove mathematically that pretty much that T does not include R in the equation. Now when you've got this particular setup, you know that the centripetal force in this example is the magnetic force, because the magnetic force is acting perpendicular to motion, so it has to be the centripetal force. So we can say that the general centripetal force equation is mv squared over r. We know that the equation for the magnetic force on a charged particle is bqv, so we can straight away equate the two. Now we can say that the time in the semicircle, which is what we need to think about for this particular equation, is distance over speed, because you know speed is distance over time, so we just rearranged it. Now the distance covered in a semicircle is pi r, because it's half the circumference, and the circumference is pi d, and r is half of d, so therefore the distance of the semicircle is pi r. So what we can say is that T equals pi r over v. Now we've got r from our equation bqv equals mv squared over r, so we can substitute that value in and then make r the subject and put time in the equation. We can then rearrange it all and get that the time in the semicircle is going to be equal to pi m over bq. Now you'll notice in this situation r is not present, so therefore it must be independent of each other. Now what you can do for the second question is once again say bqv equals mv squared over r. Why can we do that? Because in this example the magnetic force is acting as the centripetal force. We can rearrange it and we can make v the subject. So we can say from our equation that v equals bqr over m, because we've just cancelled out some terms and made v the subject. You've got b in the question, it's 0.44. You've got q because you know it is a proton, so the charge is 1.6 times 10 to the minus 19. That's just a fact you've got to know. And we know r from the question is 0.55, and we know that if we look at that mass of the proton, you've given it in the equation book, 1.67 times 10 to the minus 27 kilograms, so you get our answer to be 2.3 times 10 to the 7. The next question says, state Lenz's law. Then Lenz's law can be demonstrated using a bar magnet and a coil of wire connected to a sensitive ammeter as shown. The bar magnet moves towards the coil and is then brought to a halt. State how the reading on the ammeter changes during this process. Then during the demonstration, an induced current is detected by the ammeter. The induced current is in the direction E to F. Explain how this demonstrates Lenz's law. So pause the video now, then unpause the video when you want to go through your answer. Right, so the first one is just a fact. You've just got to learn Lenz's law, and that is that the direction of the induced EMF, which is produced with a change in flux linkage, is going to oppose the change in flux linkage that is producing it. The magnitude law is Faraday's law, the direction law is Lenz's law. Now in this next question, we can use this idea to actually understand from Faraday's law what's actually happening to the reading on the ammeter. And what happens in this process is that there will be a reading on the ammeter when the magnet is moving towards the coil, because when it's moving towards the coil, it's changing how many field lines it cuts through. Well, the coil cuts through because the magnet's changing how close it is to the coil, so therefore there's a change in magnetic flux linkage, so therefore there will be an induced EMF and therefore a current produced in the circuit. However, when the magnet stops moving, whilst there's still a flux linkage because the coil is still in the magnetic field of the bar magnet, there's no longer a change in flux linkage because it's not changing, because everything's staying stationary, so there's no induced EMF, there's no current, and there's no reading on the ammeter. Now it says during the demonstration, the induced current is detected by the ammeter, and the induced current is in the direction E to F. Explain us how this demonstrates Lenz's law. Well, if you think about it, the induced current is going to produce a north pole on the right hand side of the coil, if you think about what's going on, which is going to oppose the motion of the magnet, and you'll get that repulsive effect. Now this is important because it tries to maintain a small magnetic field as the magnet approaches the coil, so it indicates the idea of Lenz's law. So let's have a look now at a few questions on gravitational fields. So the first question says, define the gravitational potential at a point and then explain why gravitational potential is always a negative. So pause the video now, then unpause the video when you want to go through your answer. Right, the first two questions are just literal definitions you've just got to learn. So gravitational potential, and this is a 2-mark definition, is the work done per unit mass, because gravitational fields are always per unit mass, in moving the massive object from infinity, from outside the field, to a point inside the field. Now, why is gravitational potential always negative? It's because we define gravitational potential to be 0 at infinity. So outside of the field, the energy that the object has per unit mass is 0. Now that tells us we've got to put work in when the object's in the field to get out of the field, because gravity is always an attractive force, so we've got to put energy into it for the object to get out of the field. So if we're putting energy in to reach 0, it must start off as a negative value. The next question says, show that the magnitude of the gravitational potential at the Earth's surface due to the mass of the Earth is about 6.3 times 10 to the 7 joules per kilogram. Then a satellite is launched into a geostationary orbit. Describe and explain 2 features of a geostationary orbit. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we've got to look at our equation for gravitational potential, which is found in our equation booklet, and that is V, gravitational potential, is equal to minus big G, big M over R. Now, big M is the mass of the object producing the field, which is the Earth, and you're given the mass in this particular question. So we know that the mass of the Earth, okay, is going to be 5.97 times 10 to the 24. We know this because it's given to us in our equation book. We know what the value of R is. It's going to be 6.37 times 10 to the 6, because that's the radius of the Earth, because we're going from the center of the Earth to the surface of the Earth. Once again, the radius of the Earth is given to you on your equation booklet. And we know what big G is. It's 6.67 times 10 to the minus 11. Once again, that number is given to you on your examination book. So it works out to be minus 6.25 times 10 to the 7 joules per kilogram. Now the next question is just asking for some facts about geostationary orbits, which you've got to memorise. So a geostationary orbit is in the plane of the equator. It's always above the same location on the Earth, and they have the same time period as the time it takes for the Earth itself to rotate, because it's always above the same point on the Earth. It's always 24 hours above it. The next question says the satellite has a mass of 1,200 kilograms and it has a radius of its orbit of 4.23 times 10 to the 7 meters. Calculate the gain in gravitational potential energy of the satellite when it's placed in orbit from the Earth's surface, and then impulse engines are used to place the satellite into an orbit with a longer period. Discuss any changes this may make to the orbital motion of the satellite. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you've got to remember gravitational potential energy is equal to the change in potential times by the mass of the object. That's just a fact, that potential energy is the change in the potential multiplied by the mass. So what do? We work out our potential. We've already worked out our potential at the surface of the Earth from the previous question. So let's now work out the potential in this new position in orbit above the Earth's surface. So now we say V equals minus gm over r. Big G is just a number like before. The mass of the Earth remains constant. However, now the radius has changed, because what we've got to do is we've got to add 4.23 times 10 to the 7 in there. So it's now 4.23 times 10 to the 7 as our value of r. So therefore what we get is our value now is 9.41 times 10 to the 6 joules per kilogram. We then say potential energy is the change in potential, so it's the difference we just had from the previous one and now our new value, multiplied by the mass. And we know the mass of the satellite, small m, because small m is that's the object that's not making a gravitational field, it's just in it. So it's 1,200, so we get our answer to be 6.38 times 10 to the 10 joules. Now in our next question, discuss any changes using impulse satellite engines will do to put a satellite into an orbit with a longer period. So if we put it into a longer period, we've got to be aware from our equation of orbiting bodies that r cubed is proportional to t squared. So this tells us that when it's put into a longer period, if t has increased, so therefore t squared has increased, well therefore r cubed has to increase because they're in proportion to each other, so therefore the radius will increase. But also we know from circular motion that what's the link between time, okay, and speed, or we could say radius and speed. So we know that, well, mv squared over r, so that tells us therefore that v squared is proportional to 1 over r, because that entire term mv squared over r has to equal the same force, the same centripetal force. So v squared is proportional to 1 over r. So therefore when the when the radius increases, which we just worked out from our idea of r cubed is proportional to t squared, well therefore that tells us that v is going to get smaller as well. The next question says, state what's represented by gravitational field lines. Then figure 6 shows the gravitational field above a small horizontal region on the surface of the Earth. Explain why the lines converge over a small area at K. Then a ball traveling at a constant speed passes position J, moving towards position K in the figure. Explain any changes in speed of the ball as it approaches K. So pause the video now, then unpause the video when you want to go through your answer. Right, so the first one, again, is just a fact you've got to learn. Gravitational field lines show the direction that of the force on a mass. So it's the direction that a stationary mass or unit mass will move in a situation. Now you've got to think, why would the field lines converge over a small area? Well, the separation of the field lines, the field line density, is a link into the field strength. So therefore it tells us that the gravitational field around K is going to be stronger. Now it's either going to be because there's more mass in around K, so therefore you're going to have a greater gravitational field, or also that the density is going to just be bigger at around that point, which is more likely. So the answer is more likely to be that at K, that the rocks are denser, so therefore you've got a higher proportion of mass per unit volume, so therefore your gravitational field will be stronger and bigger. Now what's going to happen to the speed of the ball as it approaches K? Well, you'll notice that as the object approaches K, there's a stronger gravitational field, so there's a stronger attraction there, so the ball will speed up, it will accelerate as it moves towards K. Now again, you can see this because the potential is going to be lower at K, so therefore it'll want to get there, it'll want to accelerate towards it. The next question says, derive an expression to show that for satellites in a circular orbit, t squared is directly proportional to r cubed, and then Pluto is a dwarf planet. The mean orbital radius of Pluto around the Sun is 5.91 times 10 to the 9 kilometers, compared to a mean orbital radius of 1.50 times 10 to the 8 kilometers for the Earth. Calculate in the years the orbital period of Pluto. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, what you've always got to remember is that if an object's going in a circular orbit, well, therefore you've got a centripetal force acting on the object. And then we know in this case, because it's orbiting due to gravity, that the gravitational force is going to be the centripetal force. So we can say that mr omega squared, which is our centripetal force equation, it's just a link to mv squared over r, but with omega instead of v there, is going to be equal to g big M small m over r squared. We can then equate the two to each other. We can therefore then link it into the idea of t by understanding what t is, and that is that, well, omega is equal to 2 pi f. So we know that f is 1 over t, so therefore omega is equal to 2 pi over t. So when we say mr omega squared, we can actually write that as mr 4 pi squared over t squared. We can then rearrange it all and make t squared the subject, and we get out that t squared is equal to 4 pi squared over gm times by r cubed. Now 4 pi squared is a constant, gm is a constant, so that leaves us that the only two values that can change in the situation is t squared and r cubed, so they must be directly proportional to each other. Now the next question, if we know that t squared is directly proportional to r cubed, well, we can use that in our proportionality. So we can say that t1 over t2 all squared is equal to r1 over r2 all cubed, because they're just directly proportional to each other. Now we're given in the question the time period of the Earth, because we know it to be 1 year. Now you think, why we're using years in this question and not seconds? Well, we're doing that because it's a ratio, because it's t1 over t2 and r1 over r2. So as long as we keep it the same units, it should work through. So we know that the time period of the Earth is 1 year. We've got the radius of the orbit for Pluto, the radius of orbit for the Earth in the question. You can then make the orbital time period for Pluto to be the subject, and you work it through to be 250 years. The next question says, a small mass released from rest just above the surface of Pluto has an acceleration of 0.617 meters per second squared. Assume that Pluto has no atmosphere that can provide any resistance to motion. Calculate the mass of Pluto to an appropriate number of significant figures. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this particular question? Well, what we can say is we know what we need to work out the mass of Pluto. Now it says a small mass is released, so what we can say is we can say that F is equal to G big M, which is the mass of Pluto, the mass of the thing producing the gravitational field, times by small m, the mass of the small mass, divided by r squared. What we can then do is we can rearrange it and make it the subject by saying that big M, the mass of Pluto, is gr squared over g, big G, like that, because now we've linked it into the acceleration due to gravity, so we can link it through like that, where we can say small g is the acceleration, so we can say that, well, acceleration due to gravity, gravitational field strength, is gm over r squared. So we've now made big M the subject and pop our values in to be 1.31 times 10 to the 22 kilograms. Now again, how many significant figures do you give it to? Well, 0.617 is 3 sig figs, because you don't count the first zero. 1.19 times 10 to 6 is 3 significant figures, so your answer should be to 3 significant figures. Our next question says, figure 8 shows the variation in gravitational potential with distance from the centre of Pluto for points at and above its surface. A meteorite hits Pluto and ejects a lump of ice from the surface that travels vertically at an initial speed of 1,400 meters per second. Determine whether this lump of ice can escape from Pluto. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, there's a few different ways to answer this particular question. However, how I would tend to do it is I would work out the escape velocity of the situation. Now you can work out the escape velocity because what you can do is you can say at the escape velocity we can say that the kinetic energy is going to equal the gravitational potential energy. So we can eventually work out the escape velocity. We say half mv squared equals to gmm over r squared. We can work it out to say eventually that v is equal to the square root of 2gm over r. Now we know m, which is the mass of Pluto from the previous question. So we've got big M, we know big G, and we know what the distance from the center of Pluto is going to be by looking at figure 8. So you can work out what our distance from the center of Pluto is going to be. So therefore you can work out your escape velocity, and therefore you can work out your escape velocity is 1,200 meters per second. So that's our minimum velocity needed to escape. We're told it's leaving with 1,400, so therefore it's at a value bigger than the escape velocity, so it will leave the field. Another way you could do it is you could work out the initial kinetic energy of the object that's been ejected by doing a half mv squared. We can then work out the energy needed to escape, because you'll notice from our figure 8 we've got our gravitational potential, so we know what that value is. So therefore we can link that in by saying, well, the gravitational potential energy is going to be the mass times by the change of potential. So you can see how the potential changes when it's going from 1 times 10 to the 6 to 6 times 10 to the 6. So you can see how the potential changes. You can multiply it by your mass, which is, you can work it through like so, and then you can see what it's got enough energy to escape by comparing the kinetic energy to the energy needed to escape. So I hope you've enjoyed this particular revision session, and this revision session has been successful. So if it's been successful and you've learned in this revision session, you should be able to answer A-level physics examination style questions, assess your understanding of A-level physics, and finally understand what topics you need to improve upon for A-level physics. Thank you very much for watching this particular revision session on paper 2 for AQA A-level physics. Thank you very much for watching, and have a lovely day.